Since the earliest days of aviation, GE has built a legacy as a leading innovator of flight. That's a big part of why we're currently the largest jet engine maker in the world. Fact is, every 2 seconds, somewhere around the globe, an aircraft powered by GE technology takes off. But we're not done innovating yet. We continue to focus on and develop new technologies, working with our partners to create breakthroughs today that will inspire unimagined aviation tomorrow, and we're making more progress than ever before. One of the hallmarks of GE's current advanced technology is ceramic matrix composites, or CMCs, a once-in-a-generation materials system with benefits tailor-made for use in aircraft engines and beyond. For 20 years, GE has been at the forefront of CMC research, developing a material stronger than metal that can tolerate heat more than 500 degrees higher than any alloy, yet it weighs 2/3 less. CMCs are already at work in GE's newer jet engines and have so far racked up more than 1 million hours of flight time on commercial aircraft. Through a combination of hotter burn and lighter load, they're delivering astonishing efficiencies that translate into fuel savings, lower emissions, and better performance. The CMC difference has created a demand for this material system that is expected to grow tenfold over the next decade. Thankfully, after years of research and testing, GE and its partners have not only cracked the code to mass-producing CMC material, but have established a vertically integrated supply chain, meaning we're able to control every phase of its manufacture, from raw material production to finished parts, a reality enabling us to amplify CMC's potential, expand its availability to market, and multiply its applications for aviation and beyond. So let's take a look now at how the CMC process works. It all starts here with polysilane powder. By melting this powder, we're able to spin, cure, and heat treat it into a high-strength, corrosion-resistant, low-density silicon carbide fiber, each one only 1/5 the diameter of a human hair. The finished strands then have 4 proprietary coatings applied, coatings that enhance the fiber, that build its height, strength, and creep resistance. Next, the treated fiber is passed through a slurry of solvents, binders, and plasticizers, and spooled around a wet drum, transforming these fibers into a workable tape, large sheets of unidirectional fiber. When finished, it's on to the next phase of production. Tape is fed into a computerized machine that precisely cuts it into the sizes and shapes needed for the specific part being produced. When done, cutout plies are stacked to the desired thickness on a form or tool. The plies are oriented to use the high fiber strength properties for each layer across the thickness of the part, often alternating fiber direction through the thickness. Once all the plies are in place, the tool is put in an autoclave where low heat and high pressure transitions the layered plies into a molded part. The part then goes through a burnout process to convert all remaining organic material to carbon. The open pores created by the burnout process are melt-infiltrated with silicon to add density and complete the conversion to a SiC fiber and matrix part, capable of withstanding 2,400 degrees. Still, there's more to be done. Before CMC components can be put into service, additional work is needed to assure fit and quality. Since silicon carbide CMC is one of the hardest materials on Earth, GE uses industrial diamond drills and discs to machine and shape parts for final installation. Like all of GE's engine components, each part gets a rigorous multi-point inspection and image analysis to guarantee the physical geometrical characteristics and provide a supplemental level of precision. Finally, the integrity of the complete structure is assessed by CT scan, where any defects are discovered. From there, these parts are coated with a thermal and environmental protective. Only when all these tasks are complete, over 50 separate steps in all, is a CMC part ready for service. GE Aviation's fast and flexible CMC manufacturing process can turn fiber into finished parts, ready to go into an engine in less than 2 weeks. Large-scale CMC production, made possible by GE's vertically integrated supply chain, promises much for aviation's future. But there's more to CMCs than flying. With GE and its partners working in tandem to mass-produce this versatile material, its newfound ready availability will drive new uses. with applications ranging from interplanetary and reusable spacecraft to nuclear fuel cladding to protect modern reactors. What else? Well, who knows what tomorrow may bring. Clearly, though, for CMCs, the sky is not the limit.